I'm going to go over several examples of dynamics principles as applied to a longboarder. This first example is a situation showing normal and tangential components of a particle going around a constant radius. Here, we resolve forces and accelerations into components normal towards the center of rotation and tangentially into the direction of motion. These axes are given the names n and t and can be used to obtain the scalar equations for a particle traveling around a circle.
Here, I showed the n-axis and the t-axis. If I resolve these into their components, I get m a sub n and m a sub t. If I take the sum of the forces in the n direction, I can show that the total force in the normal direction is equal to m v squared over r, as a sub n is equal to v squared over r. For the tangential direction, I know the mass times the acceleration. Tangential acceleration is equal to dv over dt, and so I can show that the sum of the forces in the t direction is equal to m dv dt.
At this single moment in time, which can be a great keyword indicator of an F equals ma question, we can use the normal acceleration to calculate the necessary friction force required for the ground on the skateboard so that it can maintain this circular motion. By multiplying the normal acceleration by the mass of the moving particle, we can find the friction force. Since the radius is in the denominator of the v squared over r expression in the force in the normal direction equation, as the radius increases, the force that it takes to maintain circular motion is less as long as the mass and velocity stay the same. This is very apparent in the angle of the body with the ground. Between the larger and smaller radius turns, you can see a clear difference in how much the skateboarder is leaning to provide the necessarily normal force as to not fall off the board. This can be seen very easily when you overlay the images.
Now, I'm going to do an example problem using this kind of situation, where I'm given a consistent velocity of 5 feet per second, radius 1 equals 30 feet, radius 2 equals 40 feet, and the mass of the skateboarder is 75 kilograms. I'm told to find this and relate that to the force of friction on each path. First, for radius 1, I'm going to show free body diagrams for the 30-foot path, where the friction force is pointed towards the center, and I have axes of n and t for normal and tangential components. I show from a different perspective now, where the skateboarder is the particle, that there is mg, the force of gravity pointing down, the normal force pointing up, and the force of friction pointing to the center. I can then say that the sum of forces along the n component is equal to m a sub n. A sub n equals v squared over r, and so I can say that the force normal is equal to mv squared over r, which is equal to the mass, which is 75 kilograms, times the velocity of 5 feet per second squared divided by the radius, which is 30, to give 62.5 kilogram feet per second squared. Doing the same equation with 40 as the radius instead of 30 as the radius, we get that the force towards the center is 46.875 kilogram feet per second squared, which you'll notice is less than when the radius was smaller of 30 at 62.5 kilogram feet per second squared.